Surface integrals of scalar-valued functions, with examples. Before understanding how to use surface integrals, it is important to understand what a surface integral is. A surface integral of a scalar-valued function is a type of integral which can be used to evaluate the surface area of a solid in R3 space. Given some function f on a smooth surface S, we can define the function f parametrically as r of uv equivalent to x of uv, y of uv, z of uv, where u is greater than or equal to a and less than or equal to b, and v greater than or equal to c and less than or equal to d. If the tangent vectors of the curve are t sub u equivalent to the partial derivative of r with respect to u, and t sub v equivalent to the partial derivative of r with respect to v, then the surface integral is defined as the double integral of f of xyz ds equivalent to the surface integral of f of x of uv, y of uv, z of uv multiplied by the modulus of the cross product of the two tangent vectors of the curve with respect to the area, which means that the surface area of the space S can be found when f of x, y, z is equivalent to 1. Now let's do an example. Consider a torus with major radius capital R and minor radius lowercase r. The parametric description of a torus is r of uv equal to the vector big R plus small r cosine u multiplied by cosine v, big R plus small r cosine u multiplied by the sine of v, small r multiplied by the sine of u, where u is greater than or equal to 0 and less than or equal to 2 pi, and the same for v. The cross product of the tangent vectors is equal to this 3 by 3 matrix of ijk. Evaluating the determinant of this 3 by 3 vector, we get this scalar-valued function. Now we evaluate the magnitude of this vector by using the Pythagorean theorem. Using the result, we find that the modulus of this vector is equal to small r squared multiplied by the cosine of u plus small r multiplied by big R. Finally, we take the integral from 0 to 2 pi of the integral from 0 to 2 pi of r squared cosine of u plus small r multiplied by big R du dv. Solving this double integral, we get the surface area of a torus, S equal to 4 pi squared big R times small r. Surface integrals allow us to evaluate the surface areas of solids in space. While we only evaluated the surface area of the torus in this video, surface integrals can be used for spheres, cones, conic sections, and other shapes. We will go over the use of the surface integral of a vector field to calculate the flux of some region in a later video.